Suppose that n is a positive integer, then the nth moment of a random variable x is the expectation of its nth power. The moments of a random variable need not all exist. There are random variables with no first moment, i.e. no mean, for example a Cauchy random variable. There are random variables with a first moment but no second moment, etc. The point is that moments are expectations, and expectations are defined in terms of an integral, and the integrals defining the nth moment may fail to converge. In that case, the random variable y, defined to be x minus the mean of x, is a random variable with mean 0. We say that y is the centered version of x. The nth central moment of x is then the nth moment of its central version. The variance of x is defined to be the second central moment, and it's often denoted by sigma x squared, or variance of x. It's the expectation of the square of the centered version of x. It can also be written as the expectation of x squared minus the square of the expectation of x. To see this, observe that if we multiply out the inner bracket and use the linearity of the expectation operator, we obtain the following. Now, the expectation on the inside of this term here is just a constant, so by linearity it can get taken outside, and hence this middle term is equal to minus 2 times the expectation of x all squared. When we add to that another expectation of x all squared, we end up with minus 1 expectation squared. The standard deviation of x is simply the square root of the variance. It has the same units as the unit of x. Note that variance and standard deviation are both measures of how far x is expected to be away from its mean. If we have a sample point omega, in other words the state of the world, then x of omega minus the expected value of x is the distance from x to its expectation. Now if we take the mean of that, we get 0, so that tells us nothing. If we square it, however, we always get something non-negative. And so the expectation of that square is a measure of how far we expect a random draw x of omega to be away from its mean. As an example, here are 3 probability density functions. In blue we have the standard normal distribution with mean 0 and variance 1. In red we have the normal distribution with mean 0 and variance is equal to 0.5. And in green we have the normal distribution with mean 0 and variance 2. As you can see, the smaller the variance, the more peaked the distribution, i.e. the more concentrated the distribution is near its mean. So for example, the green PDF has quite a lot of mass between 2.5 and 5. In other words, there's a significant probability that a normally distributed random variable with mean 0 and variance 2 lies between 2.5 and 5. There is only a little bit of mass under the blue curve, and under the red curve there's hardly any mass at all. It is extremely unlikely that you can draw a number that lies between 2.5 and 5 if you have a normally distributed random variable with mean 0 and variance equal to 1/2. Observe that for a constant c, the variance of c times x is c squared times the variance of x, and the variance of x plus c is the variance of x. As a consequence, if x is a random variable with mean mu and standard deviation sigma, then it follows that z, defined to be x minus mu over sigma, is a random variable with mean 0 and standard deviation 1. We then say that z is the standardized or normalized version of x. All these results follow by simple computation and are left as exercises. Now we've already seen that the moments of x minus mu are called the central moments, and those of z will be called the standardized central moments. In finance, when we consider the distribution of returns, there are 2 standardized central moments that stand out. The first is the so-called skew, which is the third standardized central moment. Its heuristic interpretation is as follows. If the skewness is greater than 0, then the distribution is skewed to the right, i.e. the right tail is heavier than the left tail. Skewness is therefore a measure of asymmetry. Distributions that are symmetric about their mean will have 0 skewness. An example of this is the normal distribution. In red here we show the standard normal distribution, and we've got a negatively skewed distribution shown in blue here. As you can see, there is more mass in the left tail here. The kurtosis is the fourth standardized central moment, and it gives information about the probability of extreme events. The larger the kurtosis of a distribution, the heavier the tails. You can follow the computations on this slide yourself to show that the kurtosis of any normal distribution is 3, and therefore we usually will compute the excess kurtosis. Distributions with kurtosis greater than 3 are called leptokurtic, whereas those with kurtosis less than 3 are called platykurtic. In finance, most distributions of returns turn out to be leptokurtic. It is frequently asserted, but not necessarily true, that leptokurtic distributions are more peaked than the normal distribution. Here are 2 examples of leptokurtic distributions. The first is the usual case for financial returns. Here the standard normal distribution is shown in red. The blue curve is the PDF of a leptokurtic distribution, in this case more peaked than the normal. There is more mass near the center, in other words near the mean, but there's also more mass in the tails. In the second case, again, we have the standard normal distribution shown in red and another leptokurtic distribution shown in blue. In this case, it is not more peaked near the center, but there is more mass in the tails. As I've already mentioned, the top figure is the usual case for financial returns. It means that small returns are more likely than would be suggested by the normal distribution, but also that large positive and negative returns are more likely than would be suggested by the normal distribution. It is a stylized fact that the distributions of financial returns have negative skewness and are leptokurtic.